basically, this presentation is going to be about generating ensemble-based adversarial attack and defense methods for fraud detection. So in this process, we are going to try to find out what is so peculiar about the fraud detection landscape itself and what makes it different and interesting from the application point of view of adversarial attacks. So we'll more specifically go into why fraud is an adversarial problem and what are the kinds of ideas that fraudsters could potentially use, and can we simulate those ideas in sort of a lab environment and try to stay ahead of them in that sense. So essentially, it is trying to understand how fraudsters could attack the system, and then can we simulate those attacks. So in this process, we'll learn how to generate realistic attacks that will expose vulnerabilities in existing fraud models. And then we'll also provide limitedly some motivation around defense methods. So what could you really do to prevent or circumvent those kinds of attacks, especially in the context of temporal deterioration, which happens for fraud detection models. Over a period of time, you might see that the model loses its resolution in fraud catch. And then in those cases, it becomes more vulnerable to adversarial attacks. So what kind of defense methods can we use in that case? So quick overview of the agenda. First, we'll just provide a little bit information about the problem background and motivation, about fraud detection more specifically. Quickly go through sort of a quick sweep on the adversarial learning core concept and formulation, more specifically focus on the techniques that have been used for this particular talk. We are also going to look at the attack generation methods. So specifically 3 types of methods are used in the ensemble itself: gradient-based methods, iterative optimization methods, and generator methods. So we'll talk about the design of that ensembled adversarial attack generator. And then we'll switch to defense, where we'll use the ensemble-based framework as a seed, and then try to develop defense methods to circumvent attacks that are pretty effectively carried out by the ensemble. And we'll also look at issues related to temporal robustness. Lastly, we'll establish some conclusions on the analytical side as well as on the system performance side. So very quickly, if we actually look at the problem of fraud detection, and this is also the reason why an ensemble is applied in terms of adversarial attacks. So we'll see this more clearly as the deck rolls out. So one is, it is represented by a heterogeneous large volume payment ecosystem, which actually means you have people coming on to PayPal platform, and they are trying to do a wide range of activities, right? So they are trying to buy and sell things. They are trying to just send money. They're conducting cross-border transactions. So you see a lot of heterogeneity in the type of transactions that people are doing. And so it becomes harder to actually optimize for a context where you generate adversarial examples across the entire cohort, because in general, it is a mixture of different multivariate probability distributions. It is also multi-objective in a sense that not only are you trying to catch as much fraud as possible, you're also trying to approve as many good users as possible and as quickly as possible. You're also, in general, in terms of multi-objectivity, you also want to balance robustness with performance. So you want your model to be as robust as possible in terms of being able to catch fraud over a temporal timeline. But you also want it to be high performing. So it is guaranteed to catch a certain percentage of fraud and then approve a certain good user volume. We also have not just models, but we have strategies that run on top of models. And these strategies will typically look at locally optimal solutions. So you have a model that is serving to solve the fraud detection problem all over the world. And then you have these strategies that are in place to increase the model resolution, maybe on subsegments. And so in this case, it's also this model and strategy interplay that actually makes it harder for us to generate adversaries or adversarial examples. It's again a class imbalance problem. And lastly, there is domain-centric knowledge and strategy, as well as very complex segmentation that I was referring to earlier. So the reason why it is heterogeneous, as I was mentioning earlier, so PayPal ecosystem is really a complex social graph of consumers and merchants. And the heterogeneity really comes from 3 different questions, right? So first is, who are these people who are transacting on PayPal systems? These could be personal accounts, but these could also be merchants. And risk, appetite for risk or risk averseness is actually a function of who is actually interacting with the ecosystem. You also have the platform on which the transaction is being performed. Is it online, like is it on a browser-based system, or is it basically in-store? And then it could also be cell phone oriented. And then what are these people using PayPal for? So again, as I mentioned, there are a wide range of purposes for which people are using PayPal, including cross-border transactions. And across different countries, often different financial regulations apply as well. So in that case, we also look for optimization that happens across different kinds of subsegments. And so this also makes adversarial attack generation a challenging problem. In terms of e-commerce, it's also a large-scale problem. We are looking at close to 305 million active accounts, 2019 figure. It's much higher now post-COVID, and most people moving from paperless exchange to online exchange. Also 12.4 billion transactions, that's about 30 million per day. And then this is all happening in multiple countries, multiple currencies, and multiple funding instruments. So not only is there heterogeneity in the PayPal volume in terms of the kinds of populations that it sees, but there's also heterogeneity in the types of fraud patterns. This would mostly be, so if you were to look at it from a point of view of classification, you have basically a multivariate distribution on X. And this is heterogeneous because it is essentially a mixture of multiple probability distributions, right? Multivariate probability distributions. But at the same time, you also see that the Y, or the fraud patterns themselves, or the way the tagging is conducted in fraud detection domain, also exposes it to wide range of fraud MOs or modus operandi. Some examples could be first stolen financial, like the fraudsters could technically steal somebody's credit card or bank accounts and then channel them into a fake PayPal account and start to monetize. So now you have to really detect whether the transaction that's happening is really happening from a stolen financial versus fraudsters actually stealing identity, where you might take over somebody's PayPal account, and now you also have access to the financials. Essentially, you have access to the credit card, the bank account numbers, and so on. And so you could use that information to leverage fraud detection, malicious intents further. There's also collusion type of fraud, where buyers and sellers potentially could collude with each other in order to game the system. So heterogeneity in terms of the distributions that are generated by the ecosystem, but also in terms of the fraud patterns that are generated by the system. So how big a problem is this really in terms of obtaining credentials online in an illegal manner? So it does seem like on the dark web, what you see is there are credit cards and email and social media accounts that are sold for a price, and they go according to different buckets. So for instance, here, these are all 2016 numbers for the recent prices. And so for Visa and MasterCard, you might see that they are going at around $4 or about $7 more lately. So the idea here is basically if fraudsters are leveraging stolen instruments, and we have historical data related to certain accounts that ended up using stolen instruments, can we simulate this activity? Can we replay it back and generatively learn the patterns that actually emerged out of this market, essentially that chained in stolen instruments, namely either credit cards or even social media accounts, which are or just email addresses that are used to even create PayPal accounts. So with that, so having presented sufficient context related to the domain, let's switch gears a little bit and go back to the adversarial learning context itself. So just very quick idea here. So adversarial examples generally are essentially inputs that are designed by applying small intentional perturbations to original training examples. And what these perturbations do is, so the perturbations are deliberate and they are done through careful optimization, and they lead to an incorrect classification prediction with higher confidence. So you make a small change to the training data or the input vector that comes from the training data. In our case, it would simply be a transaction that comes through PayPal system, and then you perturb it in such a way that the transaction that was previously approved by a classifier is now declined, or vice versa, which is actually even more dangerous. So you might have potentially correctly declined a fraudster, and now through this systematic perturbation, now the classifier gets fooled into actually approving this transaction. So the idea here is to actually add so there are several ways to introduce perturbations into the context. The very simple method that can be leveraged is to essentially just add a vector with elements equal to the sign of the elements of the gradient of the cost function with respect to inputs. So if you consider traditional backpropagation method, your input is constant, and you are basically backpropagating the loss in order to find the optimal directions on the weights so that you minimize the cost. The problem in adversarial learning is flipped in a sense that now you have to keep the model. So in general, in case of black box or white box methods, if you're trying to attack a model, you let the weights or the coefficients of the model stay constant, and now you try to optimize for essentially the optimal direction in which the input should change, so that the cost function increases or it actually maximizes. So now you obtain this optimal direction in which you could switch your data, or you could sort of translate your data, so it would lead to an erroneous prediction. So let's actually look at what this means to fraud detection, right? So often what you see is fraudsters, in order to avoid being detected, fraudsters will strategize by changing status quo. So they might constantly change the assets that they are using in order to log in to a PayPal account. For example, they might actually be changing the IP address. So they might be changing either the device or the specific IP address through which they are trying to log in, sometimes even the browser. In some cases, location, that might not be that far off from where they are currently doing this transaction, online versus mobile. And also sometimes they keep channeling through different funding instruments just to see if they could get through. So, so on the one hand, this is sort of a selectively constrained problem, right? Because fraudsters can change a bunch of assets in order to get to the system, but the ways in which they change these assets are constrained, right? And I'll talk a little bit more about it as we go along in this presentation. The other way is fraudsters often try to build trust with the system, where they might start off by performing these small dollar value transactions that are successful, and this builds systemic trust. So for example, the system now starts to trust the assets through which the fraudster is trying to sign in, or let's say the IP or the device. And once enough trust is established, then the fraudster tries to capitalize by doing a large dollar value transaction, and this ends up being fraudulent. So the core idea here is, can we generate adversarial examples to fool the fraud detection model into approving a transaction that was previously declined? And then in this case, we do want to use realistically, we want to use domain knowledge in order to generate attacks that are realistic. So in the sense that you know that these attacks can actually occur, and they are well within the scope of a fraudster attempt. The other two questions that we want to answer are, one is, can you develop a monitoring and defense system that can learn, that can be learned in order to train fraud detection models and make them more adversarially robust. And lastly, as I mentioned earlier, there can be fraudulent users who start off by building trust with the system through small dollar value transactions and then try to capitalize using a large dollar value transaction. Now, if this data ends up making to your training set, this is basically data poisoning. So because potentially this guy is tagged as a good user in your training data because of the transactions that he did while doing those small dollar value transactions, which ended up being successful, but they are incorrectly labeled there. So in this case, can we identify such instances and then remediate for them using various generative techniques? So let's very quickly look at what makes this problem peculiar for fraud, right? So if you have a classic image or a speech vector, you could apply perturbation on top of that vector, and then you could assess either visually or auditorily whether this is a realistic instance or not. So there, you could use human senses in order to assess whether the example that got generated as a result of the perturbation is realistic or not. Let's move the context to fraud here. So let's assume that you have this multivariate vector, x1 through xn, and let's say the classifier actually predicts this to be a fraudulent transaction. Now let's assume there is a country-oriented variable in your multivariate vector, and that country-oriented variable could be, let's say, depicting United States. So this actually means that this transaction is happening out of a geolocation that is US. Now, let's say you perform a perturbation scheme where you try to perturb your input vector, and determine the direction in which you should change the input. So you increase the value of your cost, or maximize your cost function. So in that sense, let's say the recommendation that ends up coming as a result of that perturbation is to change that change x2, which is currently a country code of US, to maybe another country code, and that might represent, let's say, another country like Italy. So what happens here is you've applied naive perturbation to your original training vector, and you've allowed it to change in a way that makes the attack unrealistic, because the geolocation may not be possible to change the geolocation within the time range that the transaction actually occurred from one country to another. So in this case, what happens is that it's so visually, or even for that matter, using traditional methods, it is hard to actually figure out whether this is a realistic example or not. And that's the reason why we have to go back to the domain and then figure out how we can constrain the perturbation space so it generates examples that are realistic. So the key questions here are, what can the fraudster change, right? And then if the fraudster changes certain contexts, for example, let's say the fraudster changes IP. Now, sure, so you can figure out what kind of IPs the fraudster might have logged in through the time on file of the account. So the day the account got created all the way up to now, you could basically look at historically what IPs he has signed in through. But what also happens here is you have manually engineered features that might use IP as a key. So an example of this could be the number of transactions that have emanated from this IP in the last 24 hours. So this could be a fairly simple manually engineered feature. Now, if I change IP, it also impacts the value of the corresponding manually engineered feature. And then it throws you into the realm of what if. And in some sense, if the fraudster had used an IP that is potentially more hazardous, how would the manually engineered feature vector actually change? And so these are exactly the types of questions that make fraud detection very interesting from the point of view of adversarial example generation. This is also a combination of deterministic and stochastic scenarios. And you often also pick examples that might be borderline in approval. So the taxonomy of adversarial attacks is basically divided into attack and defense methods, or generally adversarial learning is divided into attack and defense methods. For the purposes of our discussion, we are going to focus very specifically on just evasion methods and limitedly poisoning methods. So the motivation for using an ensemble-based method, as I mentioned earlier, is the fact that it's a multi-objective optimization problem. But you're also trying to optimize for different characteristics, as I mentioned earlier, like in terms of, maybe you want to catch higher dollar value fraud, and that's what makes a problem interesting. In sometimes you might also want to adjust the risk appetites across different customer segments. So for example, you might have a merchant who might not have much appetite for risk. So you might have to adjust the risk threshold differently for him as compared to someone else who might be in the system for longer and is looking for more approval. Also, there are concerns about catch rate. So you want to actually have a high catch rate, but also you want to decline your good users in a way that's as optimal as possible. In our experience, what we see is different types of adversarial attacks actually discover different perturbation zones or perturbation regions. And the way we formulate this problem is to discover a maximum set cover of all of these perturbation zones that actually maximizes the exploitation of vulnerability. So in the sense, each method by itself might be lethal to some extent, but can I ensemble those methods, the adversarial attack methods, in such a way so as to get a maximum set cover of all these perturbation zones that are discovered by different regions, and then use those to attack the model with more accuracy as compared to each individual method. And so this also generates reliable and realistic perturbations, which is also one of the criteria here. And it is also required that it generates reliable and realistic perturbations. And then there are certain other criteria, like how fast you can generate these perturbations, what's the strength of the attack, what are the error rates in generating these realistic perturbations. So some methods might be pretty quick to compute, but the accuracy in terms of generating realistic perturbations might actually be fairly low. This is also the motivation for us to use an ensemble-based methods to discover these different perturbation regions and then bring them all together. So with that, so we use a bunch of methods, but what I want to do here is just sample a few, so that gives you sufficient intuition in terms of why we are using the methods that we are using. So we use a wide range of methods, and I'll actually outline them in the design, but I'll actually cover maybe one or two classes of each, so you will know exactly what we are doing. So the first method that we use is based on a gradient, which I already described earlier. Essentially, there are three different buckets of methods, the way we see it. Gradient-based, where you just compute essentially the direction in which the loss increases relative to the input. And so what kind of perturbation should you apply? So you increase the loss and then allow the model, or have the model actually come up with an incorrect prediction for a specific target. So the idea here is quite, so if, as I already mentioned with backpropagation, you basically just identify the direction and magnitude in which the parameters should change to minimize the cost function. For adversarial examples, what you really do is you try to determine the direction and in the magnitude in which the input should change so as to maximize the cost function or to increase the cost function. So one of the methods that we use is essentially the fast gradient sign method, which is fairly quick. And all you do here is you basically add the sign essentially of the gradient relative to the input, and then you use that sign to effectively and then you add a value called epsilon to the sign, essentially to generate this perturbation. We try different variations of the, so the first method is tried because of fast perturbations. It actually is probably one of the fastest methods that can yield perturbations that you could use successively. Now, when you look at evasion attack-based methods based on derivatives or based on dl by dx, there are two other variations of it that we also use. The first one is the iterative fast gradient sign method. And a quick way to really to develop some intuition about it is, so while your fast gradient sign method basically comes up with the perturbation in one shot, in the iterative fast gradient sign method actually does that iteratively. And so you don't get to what could potentially be a premature perturbation. You actually systematically look for the perturbation as sort of a search problem.
Sorry to interrupt. We thought we'd give you 5 minutes over time, or maybe a little bit more, because your talk actually ends at 2. But you know, a couple more minutes if you could wrap it up, and then we'll take any questions if we have them.
Sure, sounds good. So essentially, we use iterative fast gradient sign method and iteratively least likely method in order to basically constrain our variables either group-wise or from the point of view of bank fraud. So Kalini and Wagner is another iterative sign. It's actually a method based on iterative optimization as compared to just a dl by dx that we actually talked about earlier. The third category of method is essentially the generative method, where we don't typically, so we are not looking for either gradients or formulating the problem as an optimization problem, but we actually come up with a neural network architecture, which then generates either the examples that could be adversarial in nature, or you generate the perturbations that you can then apply to the instances to generate adversarial examples. The last category of method that we actually also use is called universal adversarial perturbations. So here we are coming up with perturbations that are input agnostic. So in the past, what you saw is every input actually generates a corresponding counterpart for an adversarial entity. But here we are actually generating perturbations that are input agnostic. So for this problem, we actually applied essentially the bank fraud scenario, where you had different sub patterns. And then what you also did was we actually looked at 3 scenarios: inadequate funds in the account, stolen bank accounts, or non-existent bank accounts. And so this was the scenario that we used in general to from a domain point of view. So this is the design of the adversarial ensemble generator method. The idea here is that we have 2 levels of optimization. The very first one is global, where we are trying to discover the most generic perturbations across different methods and across different optimization criteria. So on one case, we are optimizing maybe for high dollar value fraud. In another case, we might just be optimizing for unit fraud or just raw fraud. And the second level optimization here is actually so second level optimization is on a restricted region of the ROC. So when you have the ROC, you might not use the entire region. You might actually use maybe the riskiest K% of the ROC. So we do a second level optimization to get the most promising perturbations in a region where you already have very high confidence that these transactions are actually fraudulent. So can we change those and get the best payoff? So this is quickly comparing individual methods versus the ensemble itself. So what you can see here is there are 7 different types of methods and the ensemble. The ratio that you see is really the ratio of the model performance after perturbation and original model. So all the ratios are less than 1, which actually means that the performance has deteriorated following application of the adversarial learning method. For the ensemble itself, you see that the deterioration is actually higher as compared to the individual method. So this also brings us to the second part of the problem. Okay, so now that you generate this kind of adversarial examples, how do you mitigate against the adversarial attacks that come from those examples? So in this, what we develop is an idea where essentially you deploy the model, the champion model, and essentially the adversarial generator alongside, and then you track them with time. So what happens really is the adversarial example generator continues to track vulnerabilities in the model over time, and then it flags those changes and then learns the gaps as you're increasing with time, as you're actually progressing forward in time. So what you now have is you have this extra signal that comes out of this adversarial generator that you could use in order to retrain your model. So the way we conduct this retrain process is a method called, well, actually it's a combination of adversarial retrain and online hard example mining, where one, we do traditional adversarial retrain, but second, we also allow, so first we send all the examples through our network, and then by freezing the network, and then when we conduct backpropagation, we only backpropagate the adversarial examples. So the gradients now only adjust to basically better being able to suit the attack patterns or the adversarial patterns. So essentially selective backpropagation. And now what we also do is compare the performance between the ensemble method itself and the adversarial retrain. And here we do see that there is, at least for 3 time periods, and this is still a work in progress, at least for 3 time periods, we do see that there is a consistent increase in performance as a result of the adversarial retrain.
Great, Nitin, we got to wrap this up.
Yeah, so last slide, very quickly. So in terms of conclusions, very quickly, we see that this cohort of adversarial examples can be applied to domain-specific fraud detection. And we are also not only able to see reasonable generation of realistic perturbations, which is a problem very specific to fraud detection. And that's really a lot of know-how, domain know-how that goes in. And we are also now in the realm of testing adversarial defense mechanisms as we go along. Thank you so much. If there's any questions,
Great.
I'm happy to answer
Thanks very much, Nitin. I appreciate that you came and presented with us. Any questions quickly? This is our last session before a break. So you have Nitin here if anybody would like to ask anything. The other thing is, after the break, Chris Ward will be your MC. And he'll be introducing a few talks in the remainder of this session. So there's Chris there. So once you guys have a break, Chris, up to you when you want everybody to come back. I mean, the schedule was 2:15, maybe push it back by 5 minutes, 2:20.
I suppose, yeah. I just don't want to step on Critty's toes too much, so.
Yeah, I mean, up to you. So, but thank you again, and maybe you'll be around for a few more minutes, Nitin, during the break if people have questions for you in the chat.
Yeah, sounds good. And if there's anything that the audience feel they're inclined to know a little bit more in depth, happy to be here.
Sounds great. Thanks very much. Take care. Bye-bye.
Thank you. Yeah, so it seems like there's a question here from Shijian. This is about, so I acknowledge that there is a lot of information here. And so the foundational resources to share, actually, when I share this deck, I also have a references section. So you could actually refer to the references section. So it has some foundational papers that went into this research, plus also some other pointers that could be useful for you. We also, so we haven't done it so far, but for this particular project, but we also have a blog, an AI blog on which we publish articles, and it is also linked on the presentation. It's on Medium. So when you get the presentation, you'll also be able to get access to the blog. So we do plan to post a write-up to this particular method in details in the coming weeks. But we also have other fraud detection, fraud and also NLP related articles so far. So please feel free to check that one as well.